Section 5.2 Natural Log and Integration. In 5.1, we learned the derivative of the natural logarithmic function. So in 5.2, we will learn reverse operation, which will let us integrate rational functions of the form u prime over u. Integrals leading to natural log. Since derivative of ln absolute value of u was u prime over u, it follows that the corresponding integration would be integral of 1 over x dx is equal to ln absolute value of x plus c. Integral of 1 over u du is equal to then ln of absolute value of u plus c. Why do we need to put absolute value there? Recall, derivative of ln x was equal to 1 over x, provided that x was positive. Derivative of ln u was equal to u prime over u by chain rule, provided that u was positive. So when you go back from 1 over x or u prime over u to ln x or ln u, it is your job to designate that your input is positive. So key point here is get the numerator to be the derivative of the denominator so that your integrand becomes du over u. And whenever you have a du over u as your integrand, then it will lead you to ln absolute value of u plus c. So here we go. Let's do an example. What is the integral of 1 over 3x plus 2 dx? So my denominator is linear expression and my numerator is constant. And as far as your denominator is linear expression, any constant on the numerator is okay since we can always adjust the constant, no problem. So let u equal the denominator, 3x plus 2. So then du is, take the derivative of that, you get 3 dx. And you don't have a 3, but since 3 is a constant, you can always make a constant multiply by 3 on the numerator and divide by 3 outside of the integral so that it is quantity 1. But now you have 1/3 integral. This part right here, 3 dx, is your du. So you have 1 over u du now. So then, since you have integral of 1 over u du, so the result of integral then is equal to 1/3 ln absolute value of u plus c. However, since this is indefinite integral, we need to do the back substitution and we have to plug back what the u was, and u was 3x plus 2. So the answer will be 1/3 ln absolute value of 3x plus 2 plus c. Let's do the next problem. I have integral of x squared minus 1 over 4x cubed minus 12x. And since my denominator is third-degree polynomial and my numerator is second-degree polynomial, we're hoping that the numerator is derivative of the denominator, or we can adjust so that numerator is the derivative of the denominator so that we would have u prime over u. So let u be equal to my denominator, 4x cubed minus 12x. So then my du would be 12x squared minus 12 dx. And my x squared minus 1 dx would be same as my du if it was multiplied by 12. So no problem. Let's go ahead and multiply by 12 then, and then divide by 12 outside so that it is equal to the original expression. And now this become then 1 over 12 integral 1 over u du again. So then it is equal to 1 over 12 ln absolute value of u plus c. And since u was 4x cubed minus 12x, we do back substitution. I get 1 over 12 ln absolute value of 4x cubed minus 12x plus c. Find the area under the curve fx equal 1 over x ln x on the interval 2 to 4. Well, this is definite integral now since we're getting the area on the interval 2 to 4. So then area is equal to integral 2 to 4 1 over x ln x dx. Well, I don't know how to integrate this, so hopefully we can do the u-sub. So what should be my u? So du is there. Derivative of ln x is 1 over x, and I do have a 1 over x. My integrand is product of 1 over x times 1 over ln x. So I'm going to let u be equal to ln x, so that my du would be 1 over x dx, and I do have it. I have a 1 over x dx right there. And since this is definite integral, we also need to change our limit. So when x equal 2, my lower limit for u becomes, since u equal ln of x, u become ln 2, and that's my lower limit. And when x equal upper limit, which is 4, my upper limit for u become ln of 4. So we're ready for substitution. Then this is equal to integral. What is my lower limit for u? That is ln 2. What's my upper limit? ln 4. And 1 over ln x is my 1 over u. And 1 over x dx is my du. Very nice. And integral of 1 over u du is ln of absolute value of u from ln 2 to ln 4. So when I plug it in, I get ln absolute value of ln 4 minus ln absolute value of ln 2. So if you're looking for exact solution, this is the answer. If we would like to use approximation, you can use calculator, and this would give you approximately 0.693. Let's integrate 1 over x times ln x to the 8th power dx. This looks very similar to what we just did, except we had a 1 over x times ln x, but now this is x times ln x to the 8th power. But whenever you have ln input to the power, we can use properties of a logarithm. The logarithm has a beautiful property such that power of input come down to the front as a constant multiple. So we're gonna bring 8 down. So this become integral 1 over x times 8 comes down to the front. It become 8 times ln x dx. So then this is 1 over x times 1 over 8 times 1 over ln x. So 1 over 8, since it's a constant multiple, we could pull out in the front of integral. So now we have a 1 over 8 integral of 1 times x ln x dx. So it became same as what we had before. This is piece of cake now, right? So what is my u? My u is ln x. So then du is 1 over x dx, which I have it right there. So then this become 1 over 8 integral 1 over u du. And when you integrate 1 over u, I get ln absolute value of u plus c. And since my u was ln x, my answer would be 1 over 8 ln absolute value of ln x plus c. And that is my answer. Integrals of the trig functions. Now we can find out what's the integral of tangent x dx is. What's tangent x? As you know, tangent x is equal to sine x over cosine x, correct? So this is the integral of sine x over cosine x dx. Got an idea already? Of course. So we are going to let the denominator to be u. So let u be cosine x. Then what's the derivative of cosine x? Derivative of cosine x is negative sine x dx. So all I have to do is multiply by negative 1 on the top and then multiply another negative 1 outside so that it is the same as original expression. So then this is equal to negative 1 sine x dx is your du. 1 over cosine x now is 1 over u du. So then this is negative ln absolute value of u plus c. And my u is cosine x. So now you know integral of tangent x is negative ln absolute value of cosine x plus c. What would it be integral of cotangent x dx? That would be really easy too, right? So then this is integral of cotangent x is cosine x over sine x dx. So you're gonna let your u be sine x so that the u is cosine x dx. So then your integral is 1 over u du, which is equal to ln absolute value of u plus c, and my u was sine x. So my final answer is ln absolute value of sine x plus c. Getting really, really easy now, yes? Now, what would be integral of secant x dx? It's not that simple this time. We cannot change this to 1 over cosine x because then my denominator is cosine x and you need the du and your du would be sine x and you don't have a sine x and we cannot create a function. We can only create a number. So that's not gonna work. And what we need to do is a little bit of a manipulation so that I would have a u prime over u. And this is one of those tricks that you need to see it once, otherwise you would never think of it. So then this is equal to secant x times, I'm going to multiply secant x by quantity 1. And my quantity 1 is secant x plus tangent x over secant x plus tangent x. Why? Why? So that my numerator become du of my denominator u. All right? So then, since the secant x is secant x over 1, you need to distribute it. So you get secant square x plus secant x tangent x over, now I'm going to rewrite secant x plus tangent x as tangent x plus secant x dx. So then you can see if you let your denominator be u, let u be tangent x plus secant x, then your du is, what's the derivative of tangent? Yes, secant square x. And what's the derivative of secant? Secant x, tangent x, dx. And that's exactly what you have on the numerator. This is y. So remember the trick. So then this is equal to, now, very simple, 1 over u du, which is equal to ln absolute value of u plus c. But then, what is my u? My u is tangent x plus secant x, absolute value plus c, and that is my final answer for integral of secant x. So you know now integral of secant x is ln absolute value of tangent x plus secant x plus c. Now you know how to do the integral of cosecant x dx. So let's go ahead and do that. It's very similar and you would know how to do that. What would it be? Integral of cosecant x dx. I'm going to multiply cosecant x by quantity 1. And of course, you're gonna multiply by cosecant x plus cotangent x over cosecant x plus cotangent x dx. Then you multiply numerator with the numerator, you get cosecant square x plus cosecant x cotangent x over, I'm gonna write cotangent x first and cosecant x second so that they lined up with their derivatives. Okay, so I'm going to call my ub the denominator, which is cotangent x plus cosecant x. So then my du is equal to, what's the derivative of cotangent x? That's negative cosecant square x. And what is derivative of cosecant x? That's negative cosecant x cotangent x. So then all I have to do is multiply my numerator by negative 1. And then multiply outside by negative 1 as well. So then this becomes negative integral of 1 over u du, which is equal to negative ln absolute value of u plus c. And what was my u? My u is cotangent x plus cosecant x plus c. And that is my final answer. Summary of the trig function integrals. You have all 6 now. Integral of sine is negative cosine x plus c. Integral of cosine x is sine x plus c. Integral of tangent x is negative ln absolute value of cosine x plus c. Integral of cotangent x is ln absolute value of sine x plus c. Integral of secant x dx is ln absolute value of secant x plus tangent x plus c. Integral of cosecant x dx is negative ln absolute value of cosecant x plus cotangent x plus c. Alright, so let's do an example. Integrate integral of cosecant square root of x over square root of x dx. And you can see derivative of square root of x is not cosecant square root of x. So my u is not going to be the denominator. Instead, you look at the numerator this time because typically we do u sub for composition of functions. Now I have a cosecant of square root of x. So this is clearly composition of a function. Outer function is cosecant, inner function is square root of x. So let's try to set u equal square root of x. Then my du would be equal to, since the square root of x is x to the 1/2 power, my du is then 1/2 x to the negative 1/2 dx, which is 1/2 radical x dx. And now I go back and look at it. I do have a square root of x in the denominator. And I don't have a 2 in the denominator, but that's no big deal. We can always create that. So we can actually do u-sub for this. And because 2 is missing from the denominator, let's create 2 here. And then you can multiply by 2 since you created a 2 in the denominator, which is 1/2 really. So if you multiply outside by 2, then 2 times 1/2 is 1. And now this is twice the integral of, I have a cosecant of u, and the rest of these makes du. And I do have an integral of cosecant x dx. We just learned that today. And that is twice, and it is negative. So actually I can put -2 ln absolute value of cosecant u plus cotangent u plus c. And since my u was radical x, we can do back substitution now. So my final answer will be -2 ln absolute value of cosecant square root of x plus cotangent square root of x. And that is the final answer. Next example. Integral of 2x cubed plus 7x over quantity x squared plus 3 dx. So how would you integrate problem like this? And I don't see a composition of functions here. I have a polynomial over polynomial. But then this is not u prime over u either, since my numerator has a higher degree than the degree of denominator. So then what do we do? So when you have a rational function where your numerator has a higher degree than the degree of denominator, then you would need to do the long division to simplify the integrand. Do the long division and rewrite this as a quotient plus the remainder over your original divisor. So let's go ahead and do the long division. I have a 2x cubed plus 7x. I left the spot here because this polynomial is missing degree 2. And I'm going to divide by x squared plus 3. So when I multiply x squared by 2x, I will get 2x cubed. And then when I multiply 3 times 2x, I do get 6x. And when I subtract, this is gone, and I get x only. And since my remainder has a degree less than the degree of divisor, my long division is over. So I can rewrite this quotient as integral of quotient is 2x plus my remainder is x over my divisor was x squared plus 3 dx. What I have as an integrand now and my original integrand is the same. It is just different way of writing it. But now I can integrate 2x no problem. And I can also see that I could integrate x over x squared plus 3 since I can let my denominator be u and du would be just 2x dx. Let's integrate this now. Integral of 2x is 2 times x squared over 2 plus, let's only do the integral of this by u-sub now. So then this is canceled. And now we're going to integrate x over x squared plus 3 dx. And since my numerator now is degree less than degree of denominator, we're going to let u be x squared plus 3. Then du is 2x dx. I do have an x, so all I need is 2 here. So I'm going to divide by 2. So then this is x squared plus, I have 1/2 integral of 1 over u du. So then that's x squared plus 1/2. Integral of 1 over u du is ln absolute value of u plus c. And now I need to do the back substitution. And my u was x squared plus 3. However, can x squared plus 3 be ever negative? No. X squared is greater than equal to 0 plus 3 is always greater than equal to 3. And because it's always a positive value, we don't need that absolute value. So you are going to rewrite your answer as x squared plus 1/2 ln x squared plus 3 plus c, and that is your final answer. So note that you do need the absolute value when your answer is ln of absolute value of u when it is from integral of 1 over u du. However, when the input for ln is for sure positive, it is your job to rewrite it without absolute value. Guys, using polynomial long division to simplify and do the integration, problem like this will be for sure on the test, so make sure you know how to do it. Okay then guys, this is everything for this section, and I will see you in next section.